Hello all, today we're going to be looking at Working with Taylor series. The first one that I would like to talk about is called the binomial series. You may have heard of the binomial theorem if you took statistics. It is okay if you haven't. Basically, it is ways of being able to count things. So I know that this can actually look kind of intimidating over here, but it is a way to expand binomials. Binomials meaning like I have two, I have an x, and I have a one inside of here. So there are ways to expand binomials. The term that has no x, there's an x squared, an x to the third, and an x to the fourth kind of makes sense, but like where do those values actually come from? And we can look at that with what we call Pascal's triangle, which is a really cool way to be able to remember the coefficients that are out in front of those terms. So for example, it starts with a 1, and then I get my next row by adding together those values. And if I can't actually add those values together, then I am going to write ones. And so here I would have another 1 and another 1, and you can see that's in front of now our expanded version of 1 plus x. Those are our coefficients in front of there. I'm going to add together these ones to get a 2, and then there's nothing I can add over here or over here, so I have a 1. You can see these are my coefficients in front of my expanded binomial with a 2 up here. And then I can continue this pattern that I have here. There are all my coefficients. And if I continue that, I will get all the way down to this very last one that I have, a 1, 4, 6, 4, 1 are my coefficients in front of there. So this is called Pascal's triangle. Pascal was a mathematician back in the day, and he is recognized, which doesn't mean that he actually invented this. A lot of times things are named after people who were in power and not actually came up with the thing. Okay, so another way of actually coming up with those coefficients out in front are what we call, this is a combination that we have right here. So a way that we write that is like R combination N. That's in pretty much any calculator or also in Desmos to be able to find that. But I want to just look at one of these values up here. So if I am trying to find this value that I have right here, that would essentially be a 4 as my R, and then I am choosing 1. So looking at this formula that I have down here, I would have 4 factorial on the top, and then I would have a 4 minus 1 factorial on the bottom, along with a 1 factorial. This was not a very exciting example because when I rewrite this, that's just going to be a 3 factorial on the bottom, and those cancel out, so it is just equal to 4. So this is another way of writing this 4 right here. Another way that I could write this 6 is by 4 choose 2. I could write this 1 that I have, that's actually a 4. I was like, what the heck? I could write this 4 as a 4 choose 3. So all of these terms can also be written using this combination that I have. And a little bit easier formula to be able to write instead of this because there's a lot going on in the denominator. So if we think about it, these 3 factorial actually canceled out. So everything after however many r minus n values there were cancel out. So I could actually rewrite this as I'm going to multiply all the things down to where this would cancel out with what is after that. So for example, if this was like just r minus n factorial right here, and this is r minus n factorial, this is the term after, and those things are actually going to cancel out. So this is like our star. This is going to be way easier to use when we are actively doing this problem. And I didn't actually label this. This is our Maclaurin series that is expanded out. And so you can kind of think this is my nth derivative. So this is my nth derivative of that function. And if I plug in 0, it'll kind of cancel out all the terms that happened before that. We'll look at an example of that, just generally the groundwork and this notation, which is kind of crazy. We're also going to be looking at our ratio test to be able to find our interval of convergence. I want to jump straight into this example here. So I'm going to rewrite this 1 plus x, the square root of that, as the same thing but raised to the 1/2. And so when I look at my equation over here, it's raised to the r. My 1/2 is actually going to be my r. So r is going to be 1/2. And I'm really looking at here, actually expanding this out. So I'm going to take a second and just use this notation to actually rewrite this out. Instead of writing it in the summation notation, I actually just wrote it all out. So this is like where n equals 0, n equals 1, n equals 2, and then now I'm going to use this notation up here to kind of deconstruct that. You can just jump straight to this after you've done it for a while, but I just wanted to kind of compartmentalize. Okay, the first term can actually kind of be the weirdest because I'm looking at my 0th term, so there's not, it's like the term that's happening right before this, which is essentially just going to be like 1. And I know that even though I have a 0 factorial on the bottom right here, 0 factorial is actually defined as 1 so that it is not, so we can actually find it right here. So my first value is actually just going to be 1, but my 0th term is just going to be 1. But my first term, when n is actually equal to 1, that's when some interesting things actually start to happen right here. So I'm going to just have my first term, which in this case is just r. So I have one term, I have an x raised to the first, and then I have a 1 factorial on the denominator. I'm actually going to have my first two terms here for n equals 2. So my r is 1/2. Then I'm going to have 1/2 minus 1, and those are my two terms. I have x to the second, and then on the bottom here, I'm going to have a 2 factorial. I feel like you've probably started to see this pattern. For n equals 3, I am going to have three terms. So 1/2, 1/2 minus 1, 1/2 minus 2. I'm going to have an x to the third, so that's a 3, and then I'm also going to have a 3 factorial. Now I'm going to actually focus on just simplifying this down. So on this n equals 2, or my third term that I have here, my n equals 2, I have a 1/2 times a negative 1/2, which is going to be negative 1/4. I have a 2 factorial on bottom, so if I multiply by 1/2 to cancel that out, I will actually get a negative 1/8 right here in front of my x squared. I'm going to do that again with my x to the third. It's okay to definitely write down more than one step. I couldn't do that all in one step, so I subtracted the things on the inside. I'm going to have two negatives that will multiply and cancel each other out. It looks like I'm going to have a 3 on top and an 8 on bottom, but I have this lone 3 factorial, which is 3 times 2 times 1. So I have a 6 on my denominator, so I can multiply by 1/6 right there, and that is going to be what is in front of my x to the third. So I'll have 3 over 48, which actually just reduces down to 1/16, if I'm correct. So this is interesting here because I do have a pattern. It is alternating. This 1 is the only thing that is kind of weird here. So I'm actually going to write it separate from I'm trying to get to summation notation. So I'm going to have 1 plus, and then I am going to start with my summation right here at this 1/2 x. So instead of having an n equals 0 term, I'm actually going to start at 1. So I know that my x is going to be raised to the nth power. I'm just trying to write this in a summation. And then now I have to figure out everything else that is happening in front. You may notice that this is alternating because here I had 1 negative, here I had 2 negatives, so that was going to be positive. The next one I'm going to have 3 negatives, so that's actually going to be a negative. So I will have a negative 1 raised to I usually start with the n, and then I plug in 1 to that, and then this first term is actually positive. So I either need to do an n plus 1 or n minus 1, it doesn't really matter. So now when I plug in 1 to this, I will get a positive value, which is what I want here, but my next term will be negative. Now I just kind of have to worry about like all of my terms out in front. And so I can kind of see this pattern here. I have a 2, I have an 8, I have a 16. So this is actually going to be like a 2 to the nth on my denominator that I have there. And then this next one is just a little bit funky. So if I pay attention to these values that I have right here, so like in this case it was like a 3, in my next one it would be a 5 over here, and like so on and so on. It's going to be like a 1 times a 3 times a 5 times a whatever our 2n minus 3 term is. It's kind of a funky one. Okay, so there is my binomial series. I know that was a wild ride. It feels like we're gonna have to redo it all over again. It says use a third order Maclaurin polynomial. So what that is saying is that's actually talking about this value that I did right here to my x to the third. We're gonna use that and we're gonna say like none of the other values exist. It's not gonna give us a great estimate of square root of 1.5, but it'll be good enough. And so I just copied that down here. But if I'm trying to estimate 1.5 inside of my square root, then that means that my x is going to be my 0.5. So over here, wherever I see an x, I'm actually going to plug in 0.5, and that will be my estimate that I will have using this Maclaurin series. So here is my estimate for that. If we're looking for a bound, so like how far off are we can use Taylor's theorem to actually bound that error of how far off are we from the expanded version, all like this summation that we have all the way up here. If we were to go infinitely out, how far away is our estimate? 1.2266 from that. But this isn't something that I think you're gonna have to do in your homework. So I think it's kind of silly. I'm gonna go over it fast. Because we just get this from a previous class where we've looked at Taylor's theorem to bound. So this is our fourth derivative of that series, which if we take our fourth derivative, the first three terms are, or the first, yeah, three terms are just going to cancel out. And so this is actually bounded. It has a maximum, if you look at this value of negative 15, 2 to the fourth, 1 plus x to the 7 halves. Again, you're not going to be asked to do this, so I find it kind of silly. So I'm going to replace this value with my fourth derivative of c, and we'll find that bound. So I guess this is kind of cool because we're only this far off. We're like less than 1% off with our value that we have right here. So this is also on the back side of your formula sheet. You'll actually see all these different Maclaurin series. They looked kind of intimidating at first, but now that we know some notation, it should be a little less scary. And we can always rewrite it by like starting with our n equals 0 and go to n equals 1 and n equals 2 and start to see a pattern that we have there. I also have the interval of convergence for just the regular Maclaurin series for these. And the one that we were just looking at is this binomial expansion, so like 1 plus x to the r, and there is our Maclaurin series for that. So that is extremely helpful because what we have learned from this so far is that we can actually easily take derivatives and intervals of series once they're all written out. And that can be way easier sometimes than just trying to take it of the function itself. So if I can rewrite this cosine of square root of x using a Maclaurin series up above, then I can easily take my derivative or integral, and if I do it n many times, it just deletes that many terms that I have before it because it just will send, if I'm taking my derivative, will send those to 0. So it is really actually helpful. I just grabbed my equation from up above for just regular cosine, and I'm just going to be plugging in square root of x wherever I see an x here. So I'm going to have my summation from 0 to infinity. It's still alternating, so negative 1 to the n. And then here is where I'm going to have a square root of x instead of just an x raised to the 2n all over 2n factorial. This is another reason why cosine is considered an even function, because it has all even terms when we write it as a Taylor series. We can actually simplify this down just a little bit. Nothing really changes except for this square root right here. If I square a square root, those will actually cancel out and I'll just get an x to the n. And then this is 2n factorial that I have here. Let's take a look at the convergence on x. So like quickly I can kind of look at this and view it as an alternating series test and know that this is going to converge for all of our x's that are positive right here. So my interval of convergence would be from 0 to infinity. That isn't just including the x's that are in our domain. Let's look at our b function, so sine of x squared. So again, I grabbed my function from up above, whereas cosine was an even function and it's written with all of my even exponents. Sine is an odd function and it is written, the Taylor expansion series is written with all odd exponents. So you can see that with that 2n plus 1. I'm going to go ahead and plug in x squared wherever I see an x up here. Nothing is too bad in this one. I just replaced my x up here with an x squared. And so since all of these things are in my exponent, I can actually multiply them. I should get a 4n plus 2 in my exponent. Here is my Maclaurin series for sine of x squared. We're going to do one more example, and then I'm actually going to post a different video for the last few more like applicable or physics-esque problems that you may find here. This next one is actually kind of a trick. It's pretty wild. So I am going to rewrite this in terms of something that I already know. So I know that if I take my derivative of this function that I already have written out as a binomial in its binomial expansion of its series, 1 plus x, if I take my derivative of that, I will actually end up with that over there, but it's a difference of 1/2, so then I would have to cancel that out by multiplying by 2. So I was doing a lot in my head. Taking my derivative, let's actually just try this over to the side. So if I take my derivative of this, I'm going to have to use chain rule. So that 1/2 is going to go out in front. And then I'll have 1 plus x now raised to the negative 1/2. Chain rule, I take my derivative of the inside, which is just 1, so it doesn't change it. This is almost that, except that it has an extra 1/2. So to cancel that out, I'm going to multiply by my 2, which is what this 2 is doing right here. I'm just going to grab my 1 plus, or my square root of 1 plus x series that I had before and write it here. So now I can take my derivative of square root of 1 plus x by taking my derivative of each part that I have there. My 2 is still just chilling. Derivative of 1 is actually just going to be 0. Derivative of 1/2 x is going to be 1/2. This 2 is going to come out and multiply, so I'll have 1 less 2 right here. But I'll just write it as 2 over 2 factorial times 1 over 2 squared x. Plus my 3 is going to come out and multiply, so I'll have 3 over 3 factorial times 3 over 2 to the third x squared, and then my alternating will go back and forth, but I've actually found a binomial expansion for 1 over square root of 1 plus x by taking my derivative of something that I already had. I wrote one more term in there just so we can actually see the pattern that is happening here, and now I am going to distribute this 2 to each of my terms, and since there's a 2 to the second and a 2 to the third, and this would be a 2 to the, wait, yeah, that should be 2 to the fourth. It's just going to cancel out or lower the exponent of each of those 2's. So now I can rewrite this as I'm just going to have my 1 out in front so that here when I start with my x, I'll start with my n equals 1 so that I can, not really worry about that first term. I need a bunch more room in front of this to be able to write out what this term is going to be. So now you can see like when I plug in 1, I'll have a 2, or n equals 1, I'll have a 2. When I plug in n equals 2, I will actually have a 2 to the second. So on my denominator, I'm just going to have a 2 to the m. That's kind of nice. I don't have like a plus 1 or an n minus 1 in there. This is alternating, and my first term is positive, so I am going to have a +1. No, my first term is negative because that 1 is being used over there. So I'm just going to have a -1 to the end. And then you'll start to see here, I have a 1 times 3, I have a 1 times 3 times 5. So here I'm going to have a 1 times 3 times 5 times 2n minus 1 because it's just odd numbers in there. And that is going to be where I pause. Second video, we'll pick up on some more power series solutions and more things to do with Taylor series.